Example 177. Statistics can be used to detect fraud. There is a pattern that turns up when observing the leading digit in real data as opposed to fake data like you might find in falsified financial records. That pattern is expressed by Benford's law. The table below lists the percentages for leading digits from Benford's law that we would expect to observe. It also lists the number of leading digits actually observed on a batch of 784 checks that are believed to be fraudulent. Use this data to test the claim at the 1% significance level that there is a significant discrepancy between the leading digits expected from Benford's law and the leading digits from the 784 checks. Okay, so what we want to do here is just quickly look at the data to understand what they've given us. This law basically is just something that turns out in real financial records. It turns out that when you look at actual checks, general checks, or real transactions, about 30% of them start with the digit 1, about 18% start with the digit 2, about 13 or 12.5% start with the digit 3, so on and so forth. And so what they're doing here is they're simply saying, hey, look, if 784 checks are in our possession, we should expect that if this law holds, which it does normally for financial records, we should expect about 30% of those checks to have their dollar amounts on the check start with a digit of 1, and then so on and so forth. So they've come up with the expected values by multiplying these percents times that number of checks, and we'll talk about why that makes sense in a moment. And then they're comparing that to what they actually see on those checks. It turns out that among all these 784 checks, none of them started with a leading digit of 1. So that's kind of suspicious because we expected 30% of them to start with 1 if this law holds, and that normally does hold for legitimate checks. Okay, so they ask us to test this claim at the 1% significance level, and the claim is that there's a significant discrepancy. So I'm going to go ahead and copy that down as our claim, and then from there we'll finish working out the problem as we normally do in hypothesis testing. So let's look at the claim and just express it as, I'm going to say this. I'm going to say that, in the statement of the claim, I'm just going to say a discrepancy exists. And I'm just going to do that because the sentence down here basically covers it, and we don't have to regurgitate everything that's written there, right? A discrepancy exists. And that just means that the law doesn't hold, the Benford law doesn't seem to fit this set of checks, right? So our HO, our null hypothesis, is kind of the status quo. And if this was a criminal trial, we would normally assume innocence first, right? So let's assume the same thing for these checks. We're believing them to be fraudulent. That's why obviously they're looking into them. But let's, let HO express the idea that the checks are innocent, that they're not fraudulent. And what that means is they should adhere to Benford law. And that means that the proportion of checks, and this is P for proportion, the proportion of checks that start with a digit of 1 should be 0.301 or 30.1%. And the proportion of checks that start with a digit 2 should be, according to this, 17.6%, right? So 0.176. So on and so forth, all the way up to the 9th digit. And it says in the table that the 9th digit should occur, or the leading digit should be 9 about 4.6% of the time. So the proportion of checks that will start with a 9 will be 0.046. Okay, so that's our HO, and then we'll have HA, and HA, of course, is going to express the opposite idea, so at least one of these proportions differs from its stated value there. So we'll say essentially the same as the claim, which means a discrepancy exists. You can say HA in a lot of ways. Here, I'm just going to say a discrepancy exists. However, you could also say what? That at least one of the proportions above, right, does not hold. And what I mean by does not hold, it means that it doesn't equal what it's supposed to equal. Okay, so there we have it, HO, HA. Now we would normally work on the data step, and the main thing we do in these problems, in this chi-squared goodness of fit test, what we mainly do in the data step is to get the expected values, right? But they've done that for us already, so I just want to go over how they did that. I just want to make sure that you understand what they used. So the expected values here are going to be found by doing the following. It's going to be the expected value for checks that will start with a leading digit of 1 should be equal to the number of checks, n, times the proportion that start with 1 under the null hypothesis. Remember, the expected value is you're saying, hey, what do you expect to happen if the null hypothesis is true? Well, if the null hypothesis is true, we expect 30% or so of our checks to start with a leading digit of 1. Now, since we have 784 checks, that'll be our n, and then the proportion here would be 0.301. Let's see what that works out to be when we do that with our calculator. So we're going to do 784 times 0.301. And when we're done, we get 235.984. Now that's the exact number they gave us here in our table for the expected value of checks starting with a digit of 1. So we would continue on that path, right? Dot, dot, dot. We would keep going and do all of the remaining checks in the same way, or the remaining digits in the same way, but they've done that for us here, so we're not going to redo their work. We're just going to assume that it's already been done correctly. And just to finish up here, we would have expected value for the 9th digit, and it would be, again, n times this time p9, and so that would be 784 times 0.046. And according to our table here, it says that that would work out to be 36.064. And at that point, we finished the expected values. Okay, so they've already done that for us, so we're just going to take their work and use it in the next step. Our next step after the data step is to get the test stat, right? And the test stat is a lot of work here. Remember, the test stat is going to be chi-squared for these problems, and the formula is the summation, if you recall, for the following fraction. The fraction is going to be the observed values minus the expected value squared divided by the expected value. And of course, we're going to sum from I equals 1. And in this case, we're going to do it all the way up till we get to 9, because there are 9 separate categories that we'll have fractions for. And so then we'd have these little I subscripts for every variable here. Now, to work all that out, it essentially means we're going to have the following setup. Our fractions are going to turn out to be, for the first one, it'll be the observed value for the leading digit of 1, that'll be 0, minus the expected value, which is 235.984. That'll be squared, and then you'll be dividing by 235.984. And then you'll add to that the second digit's fraction, right? And the second digit's fraction is going to have 15 for its observed value, minus its expected value of 137.984. And then you'll square that, and you'll divide by 137.984. And then we'll keep going, right? All the way down to the very last one. And the very last one here is going to be for the 9th digit, right? And for the 9th digit, we'll have an observed value of 0 minus the expected value of 36.064 divided by 36.064. So after working all of this out, you're going to end up with a solution. And the solution here I've already done because it's very time consuming to do this. And so based on the work that I've done already, let's see what that answer turns out to be. Okay, so the answer works out to be a whopping 3,650 point, let's say just 25 for round numbers, right? That number is so large, it's not really going to matter. We are not going to find a critical value that's quite this large. This is going to indicate that we should probably reject the null hypothesis. This is going to be very far into the curve and going to be in the rejection region for sure. But, just to get practice and to be certain, let's go ahead and do the critical value as our next step. So doing the critical value entails going to a table, right? And what we're going to do here is go to the chi-squared table. Remember what our drawing looks like for chi-squared. It's actually almost like the F curve, right? It's a highly skewed curve. And it'll have, a long skinny tail on the right-hand side. We're going to use that as our rejection region, right? So if it lands over here, we're going to say reject. It always starts at 0 because this is a squared value, so it's always going to be 0 as its minimum. And we're going to figure out what critical value goes here. So where does this rejection region start? And remember where what we use to look this up. We're going to use this chi-squared notation, and we're going to have the alpha value that they mentioned in the problem, which is 1%. So we'll use 0.01, and then we need k minus 1 as our degrees of freedom, where k is the number of categories that we had. So in this case, the checks could either start with the leading digit of 1, or with 2, or with 3, or all the way up to 9, right? So there were 9 different categories that the checks could start with. So we're going to use 9 minus 1, or 8, as our degrees of freedom. So 0.01 and 8 is what we have to use when we go to our table to get our critical value. So let's go there now and see what critical value we find. Okay, so we're looking for the 0.01 column, which is not on this first page, so we'll go to the second page of the table. And on that second page of the table, we see 0.01, and we want to go down to 8 degrees of freedom, and we find the answer 20.0902. Okay, so we found the answer 20.0902. Now, that critical value, while it's pretty large, it doesn't compare to 3,650. So clearly, this critical value is to the left of our test stat. In other words, our test stat falls in the rejection region. And since it lands in the rejection region, we're going to say that we reject the null hypothesis, right? So we're going to say we reject HO, and therefore we support HA. And what that means for us, of course, is ultimately that we're saying, hey, we support the claim that there's a discrepancy, that these checks look fraudulent, in fact, because they don't adhere to Benford's law. Benford's law, which is expressed in the null hypothesis here, that doesn't seem to hold. Our test stat is off the charts large. It falls into the rejection region, so we reject the idea that these checks are legitimate, and we're going to assume that there's something wrong with them. In other words, they're probably fraudulent.